13.75 billion years ago, the universe began. Why? We don't know. 380,000 years after the Big Bang. It's a very precise number. You might say, how do you know that? Well, before that time, the universe was so hot that atoms couldn't form. So you had a soup of electrically charged particles. It was just too hot for electrons to go into orbit around nuclei. So the universe was opaque to light. So you just couldn't. It was like almost like a big glowing star, if you like.
Imagine if I told you that our universe has been around forever, even before the Big Bang. It might sound pretty wild, right? Well, hold on to your hats, because renowned physicist Brian Cox is on board with this mind-bending idea.
It's interesting, this idea of the Big Bang created the universe. That's what Einstein's theory says. That's textbook cosmology, if you like. But the current textbook picture is there was a phase in the universe's life before the Big Bang, if you define the Big Bang as the hot, dense phase from which the universe appeared to sort of burst forth 13.8 billion years ago. And that phase is called inflation. So what we think happened is that before that, the universe was accelerating exponentially fast. It means it was doubling and doubling and doubling in size. And the numbers are ridiculous. We think that if you started with a universe that was smaller than a single atom, then it would be bigger by a long way than the whole observable universe, with 350 billion galaxies in it, in less than a millionths of a second. So very rapid, exponentially fast expansion. And when that stopped, all the energy that was driving that expansion got dumped into space. It heated it up. It produced the particles of matter out of which we're made and all the things that we see out there in the sky. And that's what we see as the Big Bang. So that sounds fanciful, but that's standard cosmology at the moment. The big question then is, well, what started the inflation? What stopped the inflation? How long did the inflation go on for? And the answer to that is, we're not sure. We don't know. There are theories now that suggest, as I mentioned, that there may be more than one universe and potentially an infinite number. It's a mind-boggling idea, isn't it? And I should say one extra thing. If that's true, then some of those theories say that what we call the constants of nature, so things like the strength of gravity, the speed of light, the masses of the particles, can vary from universe to universe. And then you ask the question, well, why is our universe so perfect for life? Why do stars make carbon and oxygen, the elements that you need for life? Why is everything so beautifully balanced so that living things can exist? The answer in these cases is because, well, every universe exists. Every possible combination of the laws of nature exists in different universes. So the reason we have to see a universe that allows us to exist, obviously. We could ask the question, well, how likely is that? Well, the answer, if there are an infinite number of them, is it's inevitable, because there's every possible kind of universe. And I stress that this is very speculative stuff, but the first thing I said about inflation, the idea that there was this exponentially fast expansion before the Big Bang, if you want to use that language, that's not speculative. That's mainstream cosmology. But this idea that that may lead to multiple universes is more speculative, but it's still scientifically valid, and there are people who do research into that. And again, this is an active area of research.
It all stems from a theory put forward by none other than Sir Roger Penrose, who suggests that our universe is just one in a whole cosmic lineup. Penrose's theory shakes up our understanding of time and space by proposing that there might have been universes before ours, all part of an endless cycle of creation and destruction. Picture it, countless universes popping into existence over unimaginable stretches of time. It's not about infinity with no beginning or end, but rather a series of beginnings and endings. So what does this mean for our grasp of reality? Could it be that time itself doesn't have a beginning or end? It's a mind-bending notion, but one that's worth exploring. So let's dive in and see where this rabbit hole leads. In scientific circles, Sir Roger Penrose is esteemed as a brilliant mind, with a reputation in the UK comparable to that of the late astrophysics luminary Stephen Hawking. Penrose holds a Nobel Prize and was knighted by the British Queen for her scientific achievements. One of his most controversial theories is conformal cyclic cosmology, which suggests that our universe may have originated from a previous one. This theory challenges conventional notions of time and space. Recently, the James Webb Telescope provided new support for CCC, with discoveries that contradict traditional cosmology. Let's delve into the surprises revealed by the James Webb Telescope and what they imply for Roger Penrose's CCC cosmology. Alongside the 16 galaxies that existed so early in the universe that they must precede the Big Bang, 6 black holes also emerged, exhibiting similar characteristics. Just a few 100 million years post-Big Bang, these colossal entities already surpassed 1 billion solar masses. Then, a scientific revelation shattered existing explanations. The discovery challenges previous notions about the Big Bang's timeline. While not as ancient as other findings by James Webb, this galaxy, nearly identical to the Milky Way, raises questions about established theories. Although galactic resemblances are not uncommon, it took billions of years for our Milky Way to evolve into a fully formed spiral galaxy. This newfound galaxy existed approximately 2 billion years post-Big Bang. Assuming galaxies like this one require billions of years to develop, their age stretches beyond the Big Bang. This presents a unique advantage compared to James Webb's other discoveries. Because of its proximity, analyzing the light of this galaxy is somewhat easier compared to the even older galaxies spotted by Webb. The data regarding the number of stars, their compositions, and the formations within this galaxy are more reliable. They indicate that this galaxy exhibited a level of maturity similar to our Milky Way only billions of years after the Big Bang. Have you ever pondered the idea that our Milky Way also existed in some form during the early universe? It could have been a small, irregular globular cluster at that time. Or perhaps our Milky Way is much older than previously believed and was already traversing space as a fully formed galaxy some 13 billion years ago. With an estimated stellar mass of approximately 3.9 billion solar masses, it's considerably larger than expected for galaxies of that age, although still relatively small compared to the Milky Way. However, the primary question regarding the evolution of galaxies in the early universe revolves less around mass and more around shape. The shapes of galaxies are believed to evolve through intricate merging and growth processes spanning billions of years. How does this recent discovery lend support to Roger Penrose's conformal cyclic cosmology? According to CCC, the universe didn't begin with a traditional Big Bang concept, but emerged from a previous universe, with all information about matter, stars, and galaxies already existing. Despite this, each new universe in CCC still starts with an event akin to a Big Bang. Previous cosmologies struggle to explain what came before the Big Bang. Classical physicists claim nothing happened, while quantum physics proposed a quantum tapestry of equilibrium. However, the origin of this quantum fluctuation remained unexplained until Penrose's idea offered some insights. The CCC is highly complex, so here's a simplified overview. Picture a universe much like ours, where massive black holes consume all matter. Eventually, as the last star and grain of dust vanish into these behemoths, physical forces halt. This initiates a chain reaction akin to the universe's demise. For a brief period beyond our time frame, the universe reaches complete equilibrium, devoid of measurable forces or matter. Only the black holes may persist or evaporate in this transition from death to renewal. Eventually, a new universe emerges from what we might call a spark of life, or more scientifically, a law of cyclicity. This kickstarts the creation process anew. Penrose's theory suggests that the universe's properties at its end closely resemble those at the beginning of a new era. He developed the CCC concept while exploring the core aspects of general relativity and quantum mechanics. To this day, the two disciplines remain considered incompatible. Penrose sought both points of contact and contradictions between them. In his exploration, he observed the significance of singularities and the characteristics of the cosmic microwave background. He noted that the thermodynamic time direction of the universe, as dictated by the second law of thermodynamics, could hint at a large-scale structure. Penrose posited that the universe likely originated in a state of very low entropy, indicated by the smooth and ordered state of the cosmic microwave background. Central to the conformal cyclic cosmology are the Hawking points, tiny regions within the cosmic microwave background that could be remnants of black holes from previous universe cycles. According to this model, these primordial black holes would have existed in earlier universe epochs and subsequently evaporated through radiation, leaving behind observable traces in subsequent cycles of the universe. Another interpretation suggests that black holes managed to survive the transition from one universe to another. This perspective sheds light on why the discovery of ultramassive black holes near the Big Bang lends support to Penrose's theory. If information regarding stars, galaxies, and matter formation seamlessly transferred from an old universe to a new one, it's plausible that the evolution of matter and galaxies occurred at an accelerated pace. If the CCC theory holds true, it would establish a completely new starting point, prompting questions about the true nature of time and space. This notion aligns with the concept of the cyclicity of the universe, which serves as a coherent subset of eternal inflation and the multiverse theory. Naturally, this also prompts inquiries into the fundamental characteristics of time and space. The theory of eternal inflation traces its roots back to the contributions of physicists such as Alan Guth and Andre Linde.
Inflation is a prequel to the conventional Big Bang picture. It provides a story that precedes the expansion of the universe, the formation of galaxies, et cetera, et cetera. So the way in which inflation explains the bang is in terms of a very surprising feature of physics, I think it's very surprising to most of us, which is the fact that gravity can actually sometimes act repulsively. Now, those of us who learned about gravity in high school and learned Newton's law of gravity probably think this sounds crazy, because Newton's law of gravity is purely an attractive law of gravity. But that got changed with the advent of Einstein's theory of gravity, which is the theory called general relativity. According to general relativity, gravity normally acts attractively, but there are circumstances under which it can act repulsively. And furthermore, modern particle physics very strongly indicates that at very high energies we expect there to exist the kind of states of matter that would produce the repulsive form of gravity that general relativity allows. And inflation is basically the proposal that the bang of the Big Bang, the driving force behind the expansion, was this repulsive gravity as allowed by general relativity. Once you decide that this mechanism of propulsion is very likely the way our universe was born, you can ask what kind of universe does it predict and does it agree with what we see? And in fact, it allows us to understand three very important properties of our universe. One is it allows us to understand the uniformity of our universe. As I think was already mentioned, this cosmic background radiation that has been now measured with incredible precision has fluctuations which are incredibly interesting, and we'll be talking about them tonight. But these fluctuations are incredibly tiny. They're only at the level of 1 part in 100,000. To an accuracy of 1 part in 100,000, the cosmic background radiation that we see is the same intensity in every direction that we look. The universe is just unbelievably uniform on large scales. And that cannot be understood in the conventional Big Bang picture. But inflation explains it very naturally. You start with a very small universe, which becomes uniform before inflation, and then inflation just takes over and magnifies this tiny uniform speck to become large enough to include everything that we observe.
In the 1980s, two researchers uncovered that following the Big Bang, a small portion of space experienced rapid expansion driven by a phenomenon called inflation. This inflationary period smoothed out initial irregularities, giving rise to the observable universe. However, the theory of eternal inflation suggests that this process never entirely ceases. In certain regions of space, inflation halts, forming bubble universes, while in others it persists, potentially generating an infinite array of universes. This concept leads to the notion of a multiverse, encompassing countless universes with varying physical laws and constants. Within this new framework, there could be further inflation occurring. The bubbles expand, contributing to the growth of the multiverse, where universes interact and inflation decelerates. Overall, the multiverse is depicted as a realm of continuous evolution and creation. Amidst these processes, the concept of a cyclical universe emerges, emphasizing constant renewal and expansion rather than a definitive beginning and an end. Only on much larger scales. You can picture it like on Earth. Earth is now our multiverse, teeming with billions of people, countless animals, plants, and diverse habitats. Within this vast expanse, individuals, animals, and seasons come and go, yet new life is continually emerging, making this world a vibrant expression of existence and growth. The concept of eternal inflation and the multiverse fundamentally alters our understanding of time and space. In the theory of relativity, time and space are viewed as components of a four-dimensional continuum influenced by the presence of mass and energy. While we've derived many scientific principles from this framework, we may have overlooked crucial aspects, leading us to the limits of our current tools. Will we discover the elusive theory that Albert Einstein tirelessly pursued throughout his life? The singular equation that encompasses everything the universe comprises, its origins and its mechanisms. Despite Einstein's efforts, this ultimate equation remains elusive. Scientists continue to await the discovery of this mystical formula, often referred to as the unified field formula or simply the field formula. Maybe our mistake lies in focusing on a field too narrow to encapsulate something much broader. Just as we can't describe a tree by examining a single leaf, attempting to reconstruct the entirety of the tree from a leaf's genome in a laboratory might parallel current efforts in particle physics. Scientists aim to glean insights into the overarching mechanisms from the behavior of the tiniest particles. However, this endeavor is only partly successful, as the deeper we delve into the realm of subatomic particles, the more enigmatic our measurements become. Despite peering through telescopes across a vast expanse spanning over 90 billion light-years, like James Webb capturing light that has journeyed for more than 13 billion years, we must acknowledge that our observations may be akin to a single grain of sand on a vast beach. What role did black holes play in the universe's formation? And is it possible that they were the universe's inaugural entities? The scientist Neil deGrasse Tyson offers his own intriguing perspective on this matter. According to deGrasse Tyson, we are part of this universe. We are in this universe. But perhaps even more important than these two facts is that the universe is in us. We stand on the brink of uncovering answers to some of humanity's most fundamental questions. Where did the universe originate? Who or what brought it into existence? And do we exist as part of a grand design or merely as a product of chance? Neil deGrasse Tyson, a distinguished astrophysicist and popular science communicator, suggested that the James Webb Telescope has detected indications of black holes from a previous universe. If this assertion proves true, it could imply that our universe is just one in an endless series of cosmic rebirths. Should this hypothesis be confirmed, it would necessitate a re-evaluation of the entire history of cosmology. James Webb challenges our understanding of the universe. What distinguishes a galaxy as a universe breaker? These galaxies earned this title because they seemingly existed shortly after the Big Bang, suggesting an age older than the universe itself. Now, this notion defies logic, indicating a discrepancy somewhere. With the recent discoveries by the James Webb Space Telescope, science embarks on a new frontier. Approximately 20 of these galaxies have been officially confirmed, with their age and distance meticulously verified by independent scientific teams. For the remaining candidates, calculations are ongoing, with the possibility that some may not be galaxies but enormous black holes. One such confirmed black hole, with a mass potentially exceeding 1 billion solar masses, dates back to a mere 500 million years after the Big Bang. This poses a puzzling question. How could a black hole accumulate the mass of over 1 billion suns in such a relatively short time? Especially when previous calculations suggest that only the first stars were forming during this period. Something seems very awry here, leading researchers to seek new explanations for what the Webb telescope is revealing to us. The discrepancies likely stem from the formation of matter and the calculation of the universe's age. How did matter truly originate? Quantum physicists have unearthed that nothing truly exists, meaning there couldn't have been anything before the Big Bang. Instead, the state preceding the Big Bang manifested as an absolute balance of all forces. Quants emerged, neutralized one another, and then vanished back into eternity. Then, at some juncture, there was an explosion. A previously unidentified trigger at a minuscule point ensured that a quantum could no longer neutralize itself. This marked the end of absolute equilibrium and the physical zero point, leading to the creation of something. Scientists are convinced that the singular point contained all the information and the fundamental structure of everything observable in the universe today. The Big Bang occurred in a mere fraction of a second, unleashing an astonishingly hot environment filled with quarks and gluons. This primal form is termed quark-gluon plasma by scientists. As the universe expanded and cooled, it went through a series of phase transitions, leading to the formation of the first subatomic particles. Approximately a millionth of a second after the Big Bang, quarks condensed into protons and neutrons, marking the onset of the Hadron Era and the beginning of matter. Subsequently, during the Lepton Era, electrons were produced as the universe continued to cool. About 380,000 years after the Big Bang, during the recombination era, the universe cooled sufficiently for electrons and protons to form stable hydrogen atoms for the first time. This reduced the opacity of the universe, allowing light to travel more freely through space. This event is reflected in the universe today as cosmic background radiation, which has been instrumental in shaping many theories about the universe's origin and evolution. It's considered a precise record of early cosmic events, serving as a valuable map and source of information. Scientists have uncovered clues to the Big Bang and expansion in radiation, and now this radiation may also provide evidence of another universe. Neil deGrasse Tyson's suggestion about the mass of a black hole originating from a previous universe is not without merit. With James Webb's groundbreaking discoveries, the likelihood of this theory becomes increasingly plausible. Let's delve into the origins of matter. After the initial clearing of space, matter's building blocks were evenly distributed. Gravity then began to collect these structures, causing them to condense until the first stars emerged. Previous estimates put the universe's age at 500 million to 1 billion years. However, the James Webb Telescope reveals highly developed galaxies during this period, suggesting an age of several hundred million to a billion years. Could there have been another universe? Initially deemed too far-fetched, Roger Penrose proposed the concept of a cyclical universe in one of his acclaimed books in 2010. His scientific peers were shocked. It was as if a scientist was attempting to apply Eastern reincarnation principles to the cosmos. However, Roger Penrose is no ordinary scientist. He's one of the most brilliant astrophysicists and thinkers of our era. Penrose gained even more recognition following the passing of his equally esteemed colleague and close friend, Stephen Hawking. In his home country, Penrose is just as renowned and beloved as Hawking was, having received a Nobel Prize in 2020 and been knighted by the Queen long ago. These accolades stem from his remarkable contributions to physics and his dedication to making science accessible to all. Penrose authored numerous books and aimed at elucidating complex astrophysical concepts for the general public, participated in programs for children and young adults, and appeared on various BBC science shows. When Penrose asserts something, it carries weight. A few months after initially proposing his idea, he presented a well-supported scientific paper. Penrose demonstrated that within the cosmic microwave background radiation, which has remained nearly unchanged since ancient times, there are indications of black holes that may have existed prior to the Big Bang. So what does this imply? Conformal cyclic cosmology suggests that the universe undergoes an endless cycle of successive phases or eons, with each eon beginning with a Big Bang and concluding with a state akin to a new Big Bang. Penrose contends that the concept we refer to as the Big Bang isn't an entirely new beginning, but rather a transition from one eon to another. According to the theory, this transition allows for the transfer of information into a conformal manner, preserving the spatial structure while altering the scale of time and space. Penrose also points to Hawking points in the cosmic microwave background as evidence. These regions of elevated temperature may be remnants of black holes from previous eons. The theory suggests that black holes can transmit information in the form of radiation across eon transitions, highlighting the cyclical nature of the universe. Regarding the formation of matter, the CCC offers an explanation of how matter structure and distribution change over eons while retaining partial preservation. If the universe undergoes cycles of expansion and collapse, the conditions at the end of one eon could influence the initial conditions for matter formation in the next. This suggests that the distribution of matter's basic components and the formation of stars and galaxies in the early universe were more favorable than previously believed. The fundamental matrix for stars and galaxies may have already existed, allowing the new universe to reassemble them from old structures, significantly shortening the practical construction time. This could explain why ready-made galaxies are already present just a few hundred million years after the Big Bang. Penrose's theory gains momentum with the discovery of ancient galaxies and black holes, leaving skeptics surprised at the once impossible idea. The CCC might also elucidate the early existence of black holes, suggesting they migrate between eons without significant changes and potentially play a role in the formation of new Big Bangs, akin to midwives. Surprisingly, the Big Bang resembles the double-slit experiment in quantum physics, suggesting matter forms only when measured, implying an observer in the quantum world at the universe's birth. However, how this occurred with virtually nothing present remains a puzzling question. The observer could also be pure consciousness, something akin to nothingness because it remains unmeasured and undescribed, yet it exists. Both you and I possess consciousness, which shapes matter. It's conceivable that our universe also possesses consciousness, or perhaps there exists a conscious creator. Furthermore, it's plausible that the universe employs a simple mechanism to automate transitions from one universe to another. At the conclusion of a universe, one or more massive black holes may have absorbed all matter. While Penrose proposed that these black holes would then evaporate, what if they serve as the actual origins or witnesses of new universes? Scientists from the University of Chicago and Princeton University suggest that black holes might serve as the necessary observers to collapse an undefined quantum state, leading to the formation of matter. The unique conditions at the event horizons of black holes could have catalyzed the creation of new universes. Near the event horizon, minimal radiation, named after its discoverer Stephen Hawking, is generated by the quantum entanglement of particles inside the black hole and by a small number of particles escaping the black hole. Here's the real twist. Since these few quanta, found at the periphery of a black hole, theoretically hold all the information of consumed matter, this radiation, combined with observational data, could trigger a measurement that gives rise to a new universe. This notion is especially intriguing, as it addresses the long-standing question of what becomes of all the matter and information swallowed by black holes. It's possible they're merely recycled through radiation, leading to the emergence of a new universe. Now let's shift our attention to the concept of time. The concept of time has puzzled philosophers, scientists, and theologians for centuries. From ancient civilizations to modern-day scholars, the question of whether time has a beginning has been a subject of intense debate. However, recent advancements in cosmology, particularly the conformal cyclic cosmology proposed, present a fascinating perspective that challenges traditional notions of time and its origins. As you know, at the heart of the CCC is the idea of conformal geometry, a mathematical framework that describes the shape of space-time. According to Penrose, the universe goes through successive eons, each characterized by its own Big Bang and subsequent expansion. As the universe expands, matter and radiation gradually dissipate, leading to a state of maximum entropy known as the heat death of the universe. However, instead of culminating in a singular endpoint, CCC proposes that the universe undergoes a conformal rescaling, where space-time itself undergoes a transformation that erases the distinction between the past and the future. In this conformal rescaling, the distant future of one eon becomes the remote past of the next, creating a seamless transition between cosmic epochs. This process effectively eliminates the need for a singular beginning of time, as each eon is connected to its predecessors and successors in an endless cycle of cosmic renewal. From this perspective, time is not a linear progression from past to future, but rather a cyclical phenomenon that perpetually repeats itself. One of the key arguments supporting the idea of timeless origins in CCC is the absence of a space-time singularity at the inception of each eon. In the traditional Big Bang model, the universe emerges from a singularity, a point of infinite density and temperature where the laws of physics break down. However, CCC proposes that the universe begins in a state of low entropy, gradually evolving towards higher entropy over the course of each eon. This absence of a space-time singularity suggests that time may not have a definitive starting point, but instead emerges as a consequence of cosmic evolution. But what are your thoughts on this theory? Do you believe that time is real? Let us know in the comments section below.